Today I'll be talking about our recent paper that came out near the end of last month called Semiclassics at the Cusp, where we look at using the large charge approximation in gauge theory. Okay, a bit of an outline for what we'll be doing and talking about today. I'm going to start with a bit of motivation for non-local observables, and then I'm going to tell you a bit about how semiclassical methods can be used to treat non-local observables. And then I'll talk about the results that we obtain and some possible future directions that we'd like to pursue. So maybe just to start with, the upshot is that large charge works in gauge theory. And this is a bit of a non-trivial statement, as we'll see. Usually, when we talk about large charge, we work in a theory with a global symmetry and the charges associated with this global symmetry. So a natural question is, can we extend this to gauge theory? And there are potentially some subtleties there. But in short, the answer, at least in the Abelian theories, is yes. So to start us off with a bit of motivation, here's a problem to consider. How do we distinguish between different phases of matter? So how do we know if a material is in a gaseous phase, a solid phase, a liquid phase? And the answer is, according to the Landau paradigm, is that different phases of matter are classified by the symmetries they break. So in other words, a really easy example to see this is in magnets. So if a material has a total magnetization, there is a favored direction that this magnet has, and thus we're in a symmetry broken or an ordered phase. As opposed to maybe a material, when you heat it up, it undergoes a phase transition, and if there is no net magnetism, then there's no sort of favored direction. I can flip these magnets and nothing changes. So it's symmetric. And to be explicit, we can characterize these two different phases by use of an order parameter. So this is something that is non-zero in one phase and zero in the other phase. So for example, in this magnet, we have a Z2 symmetry. So in the ordered phase, you can see there's a favored direction for the spins. And in the disordered phase, you can see there's no favored direction. So the material is symmetric if we flip it. So the total magnetization measures this. And in this ordered phase, you can see that there'll be some net magnetization. And if we heat up the material, or if we apply a strong enough magnetic field, eventually we'll encounter a phase transition where this order is broken and the symmetry is restored. So these order parameters are, our bread and butter for understanding phase transitions. And in particular, another example is something like superfluid. And in this case, instead of a discrete symmetry, this is Z2, now we have a U1 symmetry, which corresponds to conserved particle number. And in fact, this order parameter is good, but actually what we're really interested in is something a little bit weaker. And this is the notion of long-range order, which basically tells us how well do correlations persist over long distances in a material. So for example, if I pick a point in my material, and if I look really, really far away, what are the chances that, let's say, the spins will be aligned or disaligned? And in a real material, you sort of expect that over long enough distances, it's not going to be, 100% in the same in the same state, whether it's up or down. There may be some variations, but we can classify this fall off basically. So to do this, we look at this 2-point correlation function, and what we can measure then is this gamma here, which is the anomalous dimension. So classically, we expect some in 4 dimensions, a 1 on x squared fall off as we look at at large separations in our material. But thanks to quantum effects, we actually get a deviation from this classical scaling, and that's characterized by this anomalous dimension. Now, this presents us with a bit of a problem. So in superconductors, we expect the symmetry to be gauged. So we have, like in the case of a superfluid, a U1 symmetry, but this time it's a gauge symmetry. So what happens then? So we may try and use this two-point function as an order parameter to sort of classify our phase, but the problem is that this thing is not gauge invariant now. And explicitly, if you perform a gauge transformation on these fields, you basically get a factor out the front from this gauge transformation accumulated at each of these insertions. And even worse, Elitz's theorem actually tells us that this two-point function identically vanishes, which means there's no way it can distinguish between different phases because it's zero always. And you can think of this as when you take the path integral, you're averaging over all your gauge orbits. So on average, this thing becomes zero. So what you may want to do then is really sort of insist that this is a good object. So even though it's not gauge invariant and thus can't be a real physical observable, maybe you can sort of go, okay, well, we'll just gauge fix anyway and see what happens. And in this case, you can get a gauge dependent anomalous dimension, which physically can't really be meaningful because it's gauge dependent. And furthermore, you can study this object, and by Feynman diagram arguments, you actually can figure out that this anomalous dimension is gauge dependent only at the one loop level. Though I stress that this can't really be physical because it is gauge dependent. So we'd like to understand this a bit better. So one possible way to sort of get around this or resolve this issue is to dress our fields with some non-local dressing functional. So basically, we attach this extra factor to our field where this J basically satisfies this sort of conservation equation here. And the idea is that when we gauge transform A, we get like a divergence of a function. We can integrate by parts. And that hits this J to get a delta function. So we get an exponential of a phase, which exactly cancels the phase of this scalar. So then this total object is gauge invariant. And then obviously you can then look at the two-point function of this. But the problem is, again, there's lots of different ways of dressing. And in particular, we have two dressings that we'd like to think about. The first is this Dirac dressing, which basically corresponds to attaching the Coulomb field to our charges. And that's given by this equation down here, where G is just the free Green's function. And we also have this Mandelstam-Springer dressing, which is basically just attaching a Wilson line between the two scalars. And as you know, a Wilson line under a gauge transformation, the endpoints transform. So these will transform in the opposite ways to the charges so that the total object is gauge invariant. And this is just a parameterization of a Wilson line in this particular form so that it matches this dressing factor. So these dressings are really interesting. Firstly, they're good because they're gauge invariant. And there's also nice, interesting links to things like asymptotic symmetries and the memory effect. But we won't really go into that today. So the claim in the literature is that actually doing these dressings correspond to a particular gauge choice. And this would be nice because that means you can compute these gauge variant anomalous dimensions, and simply picking a particular gauge will give you a different physical observable that has some meaning. And the claim is that in the Landau gauge, we get this Dirac dressed, everything reduces to this Dirac dressing. So essentially we're computing the correlation function of fields with their Coulomb fields. And the other claim is that in this traceless gauge, we get exactly this Wilson line dressing. And this is the claim that was in the literature. So that's some motivation. Some more motivation is that these lines we can actually think about as objects in their own right. And so in particular, what we actually want to consider and study here is a more general configuration of lines. So instead of just a line between two charges, the most general thing we can do is actually study a Wilson line with a cusp. So you can think of this as like a big infinite loop. and where there is sort of like this cusp deformation, so a sharp sort of angle in our Wilson line. So, and we'll have like a charge coming in, some insertion that changes the quantum numbers of our Wilson line, and then the line going out to infinity. And explicitly in equation form, it's this correlation function. So as you can see, there's this Wilson line coming in from infinity, some insertion that changes the quantum number, and some line going out, and then a field with the opposite charge at infinity to make sure everything's gauge invariant. So given this object, what can we actually extract from it? And naturally, we also can get something analogous to this anomalous dimension called the cusp anomalous dimension. And this, we'll call it big gamma. And this sort of emerges from the divergences you get in this correlation function due to the infinite length of the line and this sort of cusp behavior here. And this is a really nice object that we can actually extract a lot of information from about our theory. So in particular, this thing gives us information about Bremsstrahlung. So as you know, when a particle is accelerated or there's a change of velocity, then radiation is emitted. And so we can actually extract information about this radiation from one of the terms in our cusp anomalous dimension. Also, we can think about these cusps as defects. And this means that we can get information about defect changing operators. So an operator living on the line that changes these quantum numbers. We also get information about the fusion of these lines. So as we take this cusp angle to be really small, we get information about how the two legs of the cusp fuse together. For example, the Casimir energy. So now we encounter a bit of another problem, is that most of the interesting systems we'd like to study are strongly coupled. So if you want to study QCD or maybe some CFT, if the theory is strongly coupled, our normal perturbative techniques fail. So what can we do? Well, one solution is to use semiclassical methods. So the idea of a semiclassical method is to introduce some large parameter that localizes the path integral. So if we can rescale our couplings and our fields in a particular way so that we can pull out some parameter out the front of our action, when we make this parameter large, our path integral is dominated by the saddle contributions. So essentially, quantum effects are strongly suppressed, and everything sort of follows a classical trajectory. So people are probably mostly familiar with this sort of idea from large N. So the idea in a large N theory is that you want some way to compensate for strong coupling, and you take a particular 't Hooft limit where you take your gauge coupling to be small, you take N to infinity, and you define a new coupling that you leave fixed. And in this large N limit, you sort of get a reorganization of perturbation theory so that all your quantities become an expansion in 1 on N. And usually these results hold for all values of these fixed 't Hooft couplings, which is nice. And this is what we call a double scaling limit. And yes, famously, in this large N limit, your Feynman diagrams become these planar diagrams, and you get a genus expansion, basically, that describes at which order these different diagrams contribute to your result. But this isn't the only way that you can introduce a large parameter into your theory. So what you can also do is restrict to the sector of large quantum number. So this could be something like spin or charge or any quantum number associated with your system. And this is also really interesting. And actually, you get a nice phenomenology out of this depending on the specific limit you take. For example, depending on the ratio of charge and spin, your system is described by these different phases such as superfluids, vortices, etc. And the power of this quantum number expansion is that it works really, really well. So once you even the leading order and the next leading order, it agrees astonishingly well with computational results, even though in theory Q should be, very, very, very large. It still holds for, well, it still gives you quite accurate results even for very, very low Q. And in fact, there's graphs that are even more impressive than this one. So the natural question is then what
By the
happens
way,
in gauge
can
theory?
I just
Yeah,
ask
yeah,
something?
yeah.
What's going on in the previous graph? What are we looking at?
Yes. So this is the scaling dimension of these operators. I think in the yeah. So this is the scaling dimension of the operator as a function of Q. So you can compute what these scaling dimensions are using a large charge method. So you've got a leading order, and then you've got once you account for the next leading order solution, and this is compared to like ladder starter and various numerical techniques.
Oh, okay, I see.
Yeah.
Looks nice. Thank
Um,
you.
there's other graphs that look even nicer. Um, Essentially, like especially in the O2 model, this is like incredibly consistent with what you would get with like lattice and stuff like that. So it really gives you results that are too good to be true. Um, yeah. So the natural question then is to wonder what happens in gauge theory. So in these other models, we have a global symmetry. So what happens if we consider a gauge symmetry instead? So there's a few things that could be funky here. And the first thing is gauge invariance. So particularly in the non-abelian theory, things are going to be much more complicated because normally when you do large charge in a non-abelian gauge theory, you look at like this maximal torus, and this gives you a set of mutually commuting charges. But a question is then in non-abelian gauge theory, what do you do? Because these charges are still not gauge invariant, and really there's not such a good notion of charge in a non-abelian gauge theory. Um, at least, well, physical states are colorless, right? And there's also the matter of, well, what operators do you study? They have to be non-local because it's a gauge theory. The next interesting question, I guess, is from the EFT point of view. So usually in the large charge picture, we expect our system to be described by a superfluid, and we can write down effective field theory for the fluctuations, which would be phonons in the superfluid. But we sort of don't expect this to quite work so nicely in the gauge theory because, well, we now have the Higgs mechanism. So normally these phonons are like a Goldstone mode, these massless Goldstone modes. But now with the Higgs mechanism, they become massive. So we don't sort of expect this EFT picture to work quite in the same way. So there's some interesting questions here. So to be precise and a bit more concrete, let's actually work with a particular model, and that will be the Abelian Higgs model. The Abelian Higgs model is nice because it's a nice model of superconductivity, and it's also one of the simplest gauged models that we can think of. It's just a gauge field and a set of scalars. And what's also nice about this is we can actually tune this to a CFT fixed point. So if you do an epsilon expansion in 4 minus epsilon, and when you work with n scalars, you can find a fixed point which corresponds to a CFT. And this means we can use nice things like the state operator correspondence. So in other words, we can compute this anomalous dimension by just computing the energy of our states on the cylinder. And so that's what we'll do here. But to do this and to use large charge, what we actually need to do is establish that we can actually come up with a semiclassical limit and that things work consistently, which is not always so trivial to do. So in particular, what we're going to do is we're going to say that our Q1 and Q2 of our lines are proportional to some large Q, where Q1 and Q2 are some order of one constants. We're going to rescale our quartic coupling, and we're going to rescale our gauge coupling and take this 't Hooft limit where the charge is large. Our electric coupling goes to zero, but this combination remains fixed. So hopefully this is reminiscent of something you would do in log_n. So then to establish an existence of a semiclassical limit, what we can do is we can write the field insertions in our correlation function in terms of an action. So, the exponential of a log is just this field again. So we essentially exponentiate and take the log of our insertions. And when we add this to our original action, we can actually rescale our fields. And we get that, yes, our action can be written in this way, where there is this large parameter q out the front of some rescaled action. And this means that when we take large q, our path integral is dominated by these classical configurations. So this is really nice. We have a semiclassical limit. Things should work. So now we can actually compute interesting quantities. So in particular, we'll compute this anomalous dimension. So at this point, what we do is we then take this scalar and we separate it into its radial and angular modes. And we also take this particular combination of the gauge field and the angular mode so that we have these gauge invariant degrees of freedom, which will be rho and b. And these are nice because this means when we work in terms of these fields, everything is manifestly gauge invariant. So because we're doing a semiclassical limit now, what we do is look at the saddle point, and we get the saddle point equations, which are just the equations of the classical equations of motion of our system, and it's these equations here. Now these are actually quite complicated to try and solve. As you can see, this has a cubic term here, so these are nonlinear equations. These are nonlinear PDEs, so quite difficult to solve. But actually, we can solve them exactly in the limit q1 equals q2. And when we do this, we can solve exactly for this gauge field, and we can compute directly the anomalous dimension by just integrating over the energy of our solution on the cylinder. And this is quite nice because this means that our anomalous dimension here has just this form, at least at leading order in Q. And this is quite interesting, as we'll see later, that this thing is completely independent of the quartic coupling. So, and there's also no higher contributions in the gauge coupling. So this is quite interesting, because I guess when you try and compute things like the Casimir energy and things like that, they'll be completely independent of your of the quartic coupling, which is an interesting result. But in general, to solve these equations, we'll need to take a G small limit and then do perturbation theory in G. But there's something else I also want to touch on, and that's, okay, we have differential equations. So to solve these, we actually need to think a bit more carefully about the boundary conditions we impose. The point is, now we have a defect, and we can potentially have some interesting non-trivial boundary conditions on this defect compared to if there was no defect. So to study this, what we can do is we can actually, from the variational principle, look at how variations look on the boundary. And to make sure variations vanish, we can consider adding a term of this form. And this is completely localized on, I guess, a small cutoff around the defect. So you can sort of think of this F maybe as like a position-dependent mass, depending on your philosophy. But the important thing is that it's a term localized on the boundary. And then what we can do is we can actually treat F as a running parameter, and we can look for fixed points. And essentially what we can do is we can find there are two fixed points, and these correspond to standard and alternate quantization. And what we want to do, though, is we want to pick this particular, we want to pick F in a particular way such that we reproduce the results of the ungauged model, which is what we expect in the G to zero limit. So in the G to zero limit, everything becomes homogeneous. So we expect something homogeneous like this one, as opposed to this other boundary condition we choose. If we take G to zero, we get something that's non-homogeneous. It depends on the angle away from the defect. So that's not what we expect in the G to 0 limit. Yeah, we work with this boundary condition. So what we do then is we want to now try and solve for these fields perturbatively in G. So instead of working with R, we'll expand. Well, instead of working with rho, we'll work with R and expand as a series in G. And we'll do the same for our B field, which we'll now call mu, for reasons that will be evident. So if we look at the leading order solution, we get exactly the results of the ungauged model. So our solution for our gauge field at our leading order is this complicated mess here. But we can see it's some non-trivial function of the quartic coupling and the charge difference. And this is a known result from the ungauged model. And the reason we call it mu is because this is what you would normally get as a chemical potential. So that's why we call it mu. And from this, you can also get the solution for the scalar. And when you compute the energy on the sphere or on the cylinder, you get exactly this contribution to the anomalous dimension. So this is really nice because essentially we didn't make any assumptions on kappa, this quartic coupling here. So this means actually this holds for any value of k that we choose, of kappa that we choose. So essentially we've done, not so much work and got the sum of every infinite Feynman diagram that you could obtain in perturbation theory around kappa equals 0. So this is really nice. Yeah. So now we can proceed to the next leading order solution. And what's interesting again is that just like the case where the charges are equal, the contribution to the anomalous dimension is independent of kappa again. So this is also really nice. Oops. Again, I stress that this is an all orders statement about perturbation theory. So at this order of the gauge coupling, and for large charge, this order in charge, there are no contributions from our Feynman diagrams. So if you did all the Feynman diagrams corresponding to this process, you would get that they all add up to 0, which is a very non-trivial statement. Then we can proceed to the next leading order solution. And as you can see, things are slowly getting quite more complicated. But again, we can do this completely analytically and compute the NNLO contribution to the anomalous dimension in the gauge coupling. And as you can see, this is now some very complicated function in terms of like hyperbolic cotangents. And this is all written in terms of this mu naught, which remember was this hideous root, which was a function of the quartic coupling as well. If we try and go further to the next leading order, we can only really do it numerically. I mean, we have the solutions for the fields that we need, but computing this energy integral is just not really tractable analytically. But we have the explicit formulas, and you can numerically integrate them. So, these long expressions maybe aren't so helpful, but what's nice is that we can actually look at the limiting regimes of small and large kappa. And if you do the typical small kappa expansion, you get something that looks like a typical perturbative series in kappa. So this is sort of what you would expect when you do a Feynman diagram expansion, and it matches what you would get. What's interesting, though, is when you look at this kappa large situation. And this is something that you can't obtain in perturbation theory. So these are really nice results at strong quartic coupling. Again, this is a bit of a mess of an expression, but what's important to look at is that we reproduce the typical sort of characteristic large charge scaling behavior that we expect in this strongly coupled limit. We usually expect something like q to the d over d minus 1, and we get this q to the power of 4/3 here. So this is nice. And I stress this is just an expansion at large kappa, and the other one was an expansion at small kappa, but we have the explicit expression that holds at all kappa. So now we have a formula that, at least in this order of the large charge approximation, actually interpolates between the weakly coupled and the strongly coupled regimes, which is very nice. So that's just the leading order in Q, right, for large Q. What we also would actually like is some of the sub-leading corrections. So this anomalous dimension will have an expansion in Q, so Q to the 0, 1 on Q, which will be suppressed as we take the large Q limit. So we'd also like to make some statements about this Q to the 0 contribution. And to do that, what we need to do is look at fluctuations around our leading order classical solutions. So what we need to do is consider these fluctuations. We obtain a quadratic Lagrangian, and what we need is essentially the eigenvalues of the inverse propagator matrix for this Lagrangian. So in this particular Lagrangian, I'll spare you the details, but it decomposes into a few different blocks. And this is one of the blocks, for example. And what we need to do then is find the spectrum of this matrix. And this is a bit complicated because, well, firstly, it's in terms of this mu and this r, which were our gauge field and our scalar field. And these things are already, from the leading order, some expansion in G. So we're already going to have to do an expansion in G because we don't know the full form of these fields. And also, these are now position dependent. So it's really not straightforward to compute the spectrum of this because these are position dependent. You have to worry about whether they commute with your derivatives and stuff like that. But this can be done. You can separate this out and compute the dispersion relations and the eigenvalue spectrum of this matrix. I'll spare you the full form of the dispersion relations because they are very long and very complicated. But what's interesting is to look at the mass spectrum you get out of this matrix. So as you can see, we get a whole bunch of different masses for our fields. And this is quite interesting because we can compare it to the U1 global case. In particular, we can look at like this S minus, for example. We can see that it is not massless and it's a function of G. So in the G to 0 limit, which corresponds to the ungauged model, these would be massless, and these actually correspond to your Goldstone bosons. So in this case, actually, the Higgs mechanism has taken place, and our massless Goldstone bosons now have a mass. And yeah, so it's qualitatively different to what we would get in the U1 global model. So yes, we have these eigenvalues of this matrix. We can go ahead straightforwardly and compute the contribution to the anomalous dimension by summing over these. And this has a very complicated form. It's in terms of these functions sigma, which is a function of these angular eigenvalues. And these are complicated, but these are known functions. But I haven't listed them here because they're very complicated. But what we can do is expand this again as a series in kappa to get a rough sort of idea of what the form sort of looks like. And you can see these are like very non-trivial functions. They're written in terms of like zeta functions and stuff like that. But I stress again, the result that we obtain is actually an exact expression in terms of this quartic coupling, even though I've written it here as an expansion in the coupling. So we have an all orders statement in perturbation theory in the quartic coupling. Okay, so I've just flashed you with some ugly expressions. What can we actually extract out of these? So let's look at some observables now. So the first thing we can look at is the defect changing operator. If we think about this line as a defect. So if we had a straight Wilson line and we add some scalar that has a different charge, we can get we can extract basically the scaling dimension of this operator living on the line as a defect. And this is given by this, if we do an expansion in alpha away from the straight line case, the part that's independent of this cusp angle gives us the dimension of this operator. And this part that's quadratic in our difference from the cusp angle away from straight gives us information about this Bremsstrahlung function. And something that's interesting or important to note is this Bremsstrahlung function is very closely related to this displacement operator. So because we have a defect, we have some translational invariance that is broken in our theory. And this is characterized by this displacement operator, which is essentially characterizes the violation of conservation of the stress tensor. And yeah, obviously, because we have some translational breaking, we're not going to have conservation here. And the idea is that, well, if we remember, this Bremsstrahlung function talks about if we have like an angled cusp, the idea is you can take an infinitesimal displacement along one of the branches of the line. So these things are very closely related. So we can go ahead and compute this defect changing operator dimension and also this Bremsstrahlung function. And if we look at this small kappa limit, we get this perturbative looking expression. And we can also do the same in the large kappa limit. And again, you see we get this typical large charge scaling behavior that we expect. What we can also do is think about the fusion. So we know that the anomalous dimension also captures information about the Casimir energy as this cusp angle becomes small. Oops. And it also has information about the next irrelevant operator living on the line as well. So you can think about this as like an OPE. As we bring these lines closer together, we get an OPE that tells us about different operators in our theory. So explicitly, we can compute, for example, the Casimir energy. And actually, this Casimir energy is independent of kappa always, which is, a very non-trivial statement as well. Maybe you would expect some quantum corrections as away from this classical Casimir energy, thanks to the quartic interactions, but that's not the case. As a caveat, though, you got to remember we are working at small g in this small g expansion. So we do expect maybe at strongly coupled g, this conclusion would change. But at least in this small g limit, this is a non-trivial result. Now we can sort of return back to our original motivation of this superconducting order parameter. And as I said before, people look at dressing this 2-point function with this Mandelstam-Schwinger dressing, which is a Wilson line between these two insertions. And the claim was that that the Dirac dressing corresponds to the Landau gauge, and that this Wilson line dressing corresponds to the traceless gauge. And actually, it's really straightforward to see that the Landau gauge corresponds to this Dirac dressing. It's a very simple integration by parts argument, but it's not so easy to see that this traceless gauge corresponds to this Mandelstam-Schwinger dressing. And in fact, it's not actually true. So this was claimed in the literature because people computed both of these quantities to O of G, and they noticed that they look the same in this particular gauge. And they conjectured that this is an exact equivalence. But we've just computed O of G squared results. And actually, as we said before, these gauge dependence can only manifest at one loop. So now we have two loop results that show that there's a difference between these two quantities, which means it's impossible that these things coincide. So we've also shown that this claim in the literature is incorrect. Okay, so basically to summarize, we've shown that large charge works in gauge theory. We've managed to establish that we can have a semi-classical limit and we can do an expansion in Q and actually compute some quantities. We've also shown that these claims in the literature about the superconducting order parameter were incorrect, and that is that this Mandelstam swing addressing is not equivalent to gauge fixing in any way. It's really a different observable. Um, and again, I guess these gauge dependent objects really don't mean anything. Um, as you can expect, we shouldn't expect them to correspond to something physical. Um, we've also been able to observe that when we have this gauge redundancy, that we don't have a type 1 Goldstone, which means that we don't really get the superfluid picture that we're used to in large charge. We get something that's a bit more complicated. And we've also been able to obtain some really nice non-perturbative results in the quartic coupling. So some further directions that we'd like to consider is now considering the same setup in the large G regime. So as you've seen, we've taken small g to be able to solve these PDEs. But we know that, obviously the same conclusions won't hold at large G. So in particular, even aside from, a convergence of perturbation theory point of view, we know that at large enough G, there's actually going to be some sort of phase transition where our classical solutions that we came up with are actually replaced by some sort of soliton. And this should change things because essentially we expected, at least at small g, that our leading order solution will be some homogeneous chemical potential. But we actually know that at the large G regime, this can't be true, and that we're going to get some non-homogeneous thing even at leading order. So at large G, we really don't expect some clear connection to the ungaged model. Another thing that would be nice to consider is non-abelian lines. It would be really nice to be able to make some non-perturbative statements about non-abelian gauge theory. But obviously, this is much more complicated. When you have non-abelian lines, now you have to worry about path ordering. So it's not exactly clear that you can just do the same sort of trick where you absorb the observables into the action and come up with a defect action. So one needs to be a bit more careful about how to do this. And then also, we also worked at a CFT. We also need to find a fixed point of the renormalization group where we can actually apply a large charge approximation. And actually finding this is not so trivial because it seems like in the non-abelian theory, we have to work at large representations, and the RG equations are dependent on your representation. As you take large representations, it's hard to engineer a limit where you get a non-trivial theory. So that's a challenge as well for the non-abelian case. It would also be really nice to consider supersymmetric extensions because people have studied things like this cusp in non-abelian gauge theories with supersymmetry. And obviously, when you have supersymmetry, you can sometimes make stronger statements. So it'd be nice to compare our work to supersymmetric techniques. And then another thing we'd like to consider is more complicated geometric setups. So things like junctions, where we maybe have multiple Wilson lines meeting in like a star shape or something, but also other geometrical configurations, like maybe a line with multiple cusps or multiple defect changing operators. And we'd like to see how much of a story we can say there. Yes, but I think that's essentially all I would like to say. So yeah, thank you for listening.
Thank you. It was very, very nice. Thank you very much. But I
Obviously,
have a
open for
question.
questions. Yeah.
Yeah, now I'm confused because I was expecting a golden boson for our superconductors, but I guess that's the difference with the gauge.
Yeah, yeah,
So
yeah.
all you mod you wrote before, does it have an interpretation in like superconductors like S? So yeah, what's all
Yeah,
that?
that's what I'm still thinking about because but
Because also
it's even
MGH is disappearing when G is zero, and so those are
e-
MS
so yeah,
minus.
so these ones are the ghosts. So That's not so much of a worry. I think it's more uh, I think it's these guys are the gauge fields. It's not so straightforward because you get mixing and stuff like this. Um, but even then, it's complicated, right? Because normally you would consider these phonons around the homogeneous background, right?
Right.
But even here, we don't have the homogeneous background because this mu is actually still some complicated configuration. But I mean, that's also a fact that we have the line inserted. So yeah, it's complicated, I think. But
Yeah.
I think actually in the case without the line though, then you should still get a homogeneous background. But then the question is like, I guess if you write an EFT for these guys, what does that mean? Um, but yeah, I think it would be something more similar to a superconductor than a superfluid, right?
Driver, you say. Yeah, but you should have like massless mode and maybe gapped mode that would correspond to.
Yeah, I guess the thing is that everything is like basically gapped.
Right. Looks like.
Yeah, I mean everything except for these, but these are just like spectator um, extra uh, extra scalar fields. So, but yeah, it's yeah,
Because when you expanded like the slide before, you said you have the dispersion relation, so you expand around which background. That's the So you have your field, you have like the background value, and then you introduce fluctuations and you get this matrix.
yeah. So we
And
expand around this like gauge field, this full gauge field solution, and this full um, radial field solution.
Mm, okay.
Yeah, but I guess it's an interesting observation compared to what you would normally expect, right?
Right. Yes. No, that's very nice.